Let's look at these questions. This is about roots of polynomial. Obtain the sum of the square of the roots of the equation. So sum of the square of the roots. Imagine that if we say that the roots of this polynomial are alpha, beta, gamma, and delta. Let's say these are the roots. So sum of the square of the root is actually, I can call it S2, is alpha square, beta square, gamma square, and delta square. So we know that S2 is equal to S1 square minus 2 sum of alpha, beta. Okay, so sum of alpha, beta is actually, you can see it from here, it is actually 5. It's 5, as you can see the coefficients of x power 2, 5. Okay, so you can put 5 here. S1 is actually minus 3, so we substitute minus 3 square minus 2 times 5, so you get 9 minus 10, which is -1. So this is the answer for the first part with 2 marks. Okay, now we continue with the second part. Deduce that this equation does not have more than 2 real roots. Okay, does not have more than 2 real roots. Okay, so to deduce this, first of all, we need to know that a quadratic equation with real coefficients this equation will have either 4 real roots, 2 real, and 2 complex, or 4 complex roots. These are the 3 possible situations. Okay, and we have to reject the first situations. We have to reject that it has 4 real roots. The reason is, if it has 4 real roots, where alpha, beta, gamma, and delta are real, and if you square the real numbers, it will become positive, 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 and positive. And when you add up the positive numbers, it should end up with a positive sum, which is not possible because our S2 is -1. Okay, so we just claim that since S2 equal to -1, it does not have 4 real roots. Okay, so this is the first thing. The second thing is, if it does not have 4 real roots, then it will have 2 real and 2 complex roots, or 4 complex roots. Okay, so hence the quadratic equations has 2 real roots and 2 complex roots, or 4 complex roots. So combining these 2 results, it means it does not have more than 2 real roots. As you can see here, so 2 real roots or no real roots. Okay, so we can just generalize it and say that it does not have more than 2 real roots. So this is the second part. Now we look at the next part. For the next part, show that in fact the equation has exactly two real roots in the interval -3 to 0. So in order to show that the real roots lies between that interval, so what we can do is we can just use sign test. Okay, so we can use sign test. So to use sign test, okay, so we build a table. We start from our polynomial. I let fx equal to x to the power of 4, 3x cubed, 5x squared, 12x plus 4. Okay, now I do sign test. I build a table. From -3 to 0. Okay, then I just substitute all this value into the quartic polynomial, as you can see here. Okay, -3, I substitute into the x's here, so I will get 13. I substitute -2, I will get -8, -5, and 4. Okay, so there is a sign change here. Sign changes, meaning that there is one real root. Again, there is a sign change here. Meaning that there is one real root. And from here, we can say that there are two real roots in -3 to 0. Okay, so we managed to show that by using sign test. Okay, now let's look at the next part. The last part. Denoting these roots by alpha and beta. So the two real roots are known as alpha and beta, and the other two roots by gamma and delta. So these two are complex roots. Show that the modulus of gamma equal to the modulus of delta is equal to 2 over square roots of alpha beta. So in order to do this, what we can see from our quartic equation is, so let's observe the last coefficient, 4. So we know that 4 is alpha, beta, gamma, and delta that multiply together. So let me write it down first. Alpha, beta, gamma, delta, multiply, and you will get 4. So let gamma equal to a complex root, in general a plus bi, and delta will be the complex conjugate a minus bi. Okay, then I substitute inside alpha, beta, a plus bi, a minus bi equal to 4 alpha beta. Multiplying the complex conjugate, I will get a squared plus b squared equal to 4. Then after that, if I rearrange this, a squared plus b squared equal to 4 over alpha beta, and after that I square root, I will get 2 over square root of alpha beta. And we have to know that, you can see it from here, our complex number gamma is a plus bi. So if I find the modulus of this complex number. So basically I have to put it in this way. So likewise, to find the modulus of delta, so a squared plus negative b squared square root, so which is a squared plus b squared. Okay, now because of this, combining all our results here, this one, and this one, they are all equal to square roots of a squared plus b squared. So hence, we can say that modulus of gamma equal to modulus of delta equal to 2 over square root of alpha beta. Okay, finish.